Hello and welcome to the Rocky Ridge Parent Math Series. We're going to be focusing on addition today. So this is also going to talk a little bit about the Alabama Numeracy Act, which is the new law that is governing how math is taught, and some important facts about elementary education and math. What we might remember is that the Literacy Act focuses on students and student achievement. It looks at student assessment and how to help kids succeed. It has an important piece in third grade dealing with the ACAP. The Numeracy Act is different, and it is focused on teachers. So it's focused on professional development, instructional moves, and database decisions, which includes hiring or the use of math coaches, which is what my job is. So Hoover was a step ahead. All of this is going to be required by 2027, but there are layers of implementation as we go. So I just like to get started and talk a little bit about old math versus new math. A lot of people want to call the way we teach math in schools new math. It's in fact not new. These ideas and strategies have been around for a long time. So we might notice that some of these algorithms that we talk about when we talk about subtraction were all considered US standard algorithms during the 40s. So the decomposition algorithm, which is the one we know and love, we might call it borrowing. The equal additions algorithm, which is known as constant difference. And then there is the Austrian algorithm, which is really is called counting back change, or starting at the small number and getting larger. And so these are all not new. These are from a long time ago. So we might ask ourselves, didn't the old way work just fine for me? If you're like me and you were raised in elementary school in the 90s, you probably learned traditional algorithms for math. And I just always like to ask people who want to say the old way worked just fine. Raise your hand if you love to read. Raise your hand if you love math. Oftentimes the response to this one is a lot less. Who among us would walk out into the world and announce that we're illiterate? No one. But when I was a classroom teacher, parents would walk in and find out that I was the math teacher for 4th or 5th grade, and they would say, oh, I was never good at math. And we don't want to make that a legacy for our kids. We want our kids to think that they can do anything. So I often ask people who say to me, didn't the old way work just fine? What's your relationship like with math? And often the response is that they don't love it. And so I would argue that the old way maybe didn't work for you. So we're going to try and change some things in elementary school. So for today, we're going to talk about addition strategies, and we're going to talk about 3 categories of strategy. All addition and subtraction strategies really can fall into one of these 3 categories. So the first category is place value, thinking about tens and ones, or of course, as you extend the magnitude of number, hundreds, tens and ones, etc., focusing on each place value. The second category is incrementing, keeping one number whole and breaking up the other number. And the third category is compensation, making an easier problem. And I'm going to really spell these out for you as we go. Here's an example of tens and ones. If we were going to add 78 and 36, you would decompose the numbers into their place value parts. So for instance, 78 is the same as 70 plus 8. 36 would be the same as 30 and 6. And then you would add the place value parts that are alike. So here I wrote it horizontally, but you could also look at, a lot of kids want to look at this problem really vertically, and they want to add in this way. So in the same way, we're going to add the ones place and get 14, add the tens place and get 100, and then you're going to put those 2 place values back together for your final total. All right, we are going to practice this strategy now. So I'm going to give you just a minute to think about these strategies. You can press pause if you need more time. All right, if you need more time, feel free to press pause. We're gonna keep moving through these strategies though. So 28 plus 47 would look something like this. Okay. 132 plus 65 can get a little hairy. So a lot of times our younger kids, as they're learning this strategy, are going to break up all the place value parts. And this is where it can get hairy, and they want to sometimes left justify and put the 60 under the 100. But we obviously don't want them to do that because that is not going to serve them here. So we're going to add, again, our place values. Okay, but I do want to just show you real quick that as kids get more proficient with this strategy, they might keep the hundreds and tens together because there are no hundreds in the second value, and be able to do something like this. And again, we're just quickening the strategy. And then as we get down here to this last problem, we've got a lot of place value, but again, I'm gonna hold on to the hundreds and thousands place for the purpose of keeping all of that together. All right, 40 and 5, 70 and 6. So we're gonna get into some weeds here. Okay, so what you may notice is as these numbers get larger, or as there's if we were doing this the old way, where there's a lot of carrying that would have to happen, this strategy begins to not be nearly as efficient. So we would see, all right, let's see. So this is going to be 3,010 plus 11, so 3,000. 21, I believe. I hope that's right. Okay, so what works about this strategy? When is it good? It's great when there's 2-digit plus 2-digit, right? It's easy and it's quick and efficient. But as we get down to some of these longer, larger in magnitude numbers, this strategy becomes cumbersome. It becomes a lot for kids to keep in mind and remember. So we want to pay attention to that. We don't want to ever leave kids in a strategy. This is a great way to begin to learn adding multi-digit numbers, but we don't want to stay in a strategy for too long. Because we want kids to be efficient. This is where kids are going to begin addition. In first grade, really, they begin to add a 2-digit number plus a 1-digit number, or some smaller 2-digit numbers like 20 plus 13 they might add in first grade using a picture, using a representation. The representation that would match this strategy is about the base 10 blocks. So if we were adding that 20 plus 13, you're going to see kids doing something like this to represent the base 10 blocks. This would represent 20. Each of these is worth 10. Okay, and then you would see something like this. Okay, and then you would see them put those 10s together and then put on the ones. Okay, so they're going to start with a model with this strategy, and the model that matches this strategy is the base 10 blocks. And then, but we don't want to leave them here. We want, eventually the goal is by fourth grade to get them to the standard algorithm that is the efficient algorithm, okay, using the carrying method. The next category is called incrementing, and incrementing is keeping one of these numbers whole and adding on by chunks. So this is, students have to understand adding tens off the decade, we call that. So for instance, if I'm going to hold on to 78, I'm going to keep 78 whole, and I'm going to break up the 36 into 30 and 6, but I may even have to break up the 30 at first into the number of tens that it is, in which case, if I was thinking about 78 plus 10, I need kids to understand that plus 10, what happens, I can count off the decade by tens quickly, right? So 88 98. I'm not completely proportional here, but 78, 88, 98, 108. That plus 30 is going to look like that. And then even adding that 6, they may decide to add to get to a friendly 10. I can add 2 more and land on 10, and then I had to add 6. I've added 2. What's left of the 6 is 4, so then I'm going to add 4 more to land on 114. So the model that matches this strategy is the number line. It's a very quick and easy model, becomes very efficient for kids. Once they understand all of this, they can just quickly draw that, maybe just add the 30 instead of 10 plus 10 plus 10. All right, so we're gonna have some time to practice this strategy. Feel free to pause if you need time. Otherwise, we're gonna move forward. What would it look like with 28 plus 47? And one thing you may have noticed on the previous slide is that we held on to 78. Now it was the first number in the of the add-ins. But in this case, the larger number is the second number. But what we want kids to understand is the commutative property of addition, that order doesn't matter. It's okay to start with the larger number because it's easier to hold on to the larger number and break up the smaller number, because then we have less work to do. So we're going to try that here with, we're going to start with 47. We're going to add 20, and that's going to get me 67. And then I'm going to add 7, but I actually might think about 7 as a 3 and a 4. And I'm going to add, oh, sorry, no, I got to add 8, a 3 and a 5, excuse me. And so, because I was adding 28. So 67 plus 3 is going to get me to 70. And then to add my 5 is a quick 75. That might look like this on a number line where I start at 47. Add 20, that gets me to 67, and then add 3 to land on that friendly 70, but I need to add a total of 8, so then I'm going to add 5 more. And my answer is 75. All right, if I'm doing the next one, feel free to take a screen capture of this if you need to. I'm going to erase it to do the next value. We're going to, again, start with that larger number. Think about that larger number. I have 132. I'm going to add 65. Now, again, I'm going to just add 60. Kids, as they're understanding this strategy, may add this 60 as bunches of tens or as some other decomposition of 60, 50 and 10, 40 and 20, something like that. Because it's not going to send us over carrying, because it doesn't carry, it's an easy one for kids to understand. 130 plus 60 is going to get me 192. That ones place stays the same because I didn't add any ones to it yet. Now I've got to add 5, and I can just add 5 to 2. It's not going to take me past a 10. And so that's an easy one on the number line. So this having an extra place value in 132 doesn't throw me off because I'm starting with that and chunking the second number. Again here, actually, I think I'm not going to do this one on a number line. We might do something like this: 2145 plus 800, 2945. Okay, and we want to keep our math sound. So we're not gonna do this. We're not gonna add 70 here. We're gonna come over here and add 70 to the right to go in this direction now. So we have 2945 plus 70, and it is gonna send us over. It's gonna change 2 place values so we might think of it as plus 60 plus 10. Okay, so if we add 60, that takes us to 3005, and 10 more equals 3015, Okay, and then what we have left is the 6. So then we're going to add 6, and we get 3,021. Okay, again, what works about this strategy? When is it cumbersome? Okay, it's a good strategy. It helps with these kinds of things. It's okay down here, but when we have to start doing all this carrying, it can get a little bit hairy. It can get what we would call cumbersome. It's a lot for kids to remember. So that is just setting the stage for a need for an efficient strategy for this type of addition, okay? Kids are not expected to do thousands until the 4th grade when they're introduced to the algorithm. The last strategy category is compensation. This is about thinking about easier numbers to add. My dad loves compensation. He uses it a lot, and you'll find probably that you might as well, because it's really about estimation and rounding. So with both of these numbers, you're going to look at them and think, am I close to a multiple of 10? Multiples of 10 are way easier to add. So somebody might look at, if I had 78 things and 36 things, and say, well, I can slide 2 of these things over here and give them to this side, and now I would have 80 things on the left and 34 things on the right, and that's a much easier problem for me to add, and I can just do that. The math looks like this, that I can take from one value and give to the other, one addend, and give to the other addend. Compensation is a give some, take some. And what we're giving, we have to take. You may also see people where they don't balance it on this side of the equation, but they balance it when they get to this side. So for instance, they would think about 78 plus 36 and change this to just be 80 plus 36, holding in their head that I have extra 2 right here. And so then when they get to the end, they take 2 off. And they would say, okay, so the actual answer to my original problem is 114 because I added 2 too many. So now I have to take that many away. Both of those are considered compensation. Take some, give some, whether you take it both from the left side of the equal sign, or if you take some, if you do some adjusting on the left side and then finish the adjusting on the right side. So you'll notice that these numbers are different. I used a different set of numbers. Feel free to pause and practice on your own. But we're going to just go ahead and jump in and talk about these. Looking at 29 plus 38, which of these would you adjust? Yeah, some people are going to say they're going to adjust 29 to 30. Some people say they might adjust 38 to 40 because both of these values are close to friendly 10. So we might say 30 plus 37, right? Take 1 from over here, give it to this side. Okay, over here, again, take 2 from here, give to here, right? You got this easy problem now, 200 plus 125, easy peasy. Okay, here you're gonna, where would you get as many zeros in a number? And it's here, right? You can take 6 and add 6. So you get 3,000 plus 1683. Oopsies, I missed a 0. And you have 4,683. Okay, easy peasy. Okay, what I would like for us to then look at is this thing called efficiency. There's a quote by a math researcher, and he says that the best way to solve a problem is dependent upon the numbers in the problem and the context of the problem. And if we go back to the original numbers that I was giving before, you might notice this first problem, no big deal, right? Take your 2, give your 2, you've got 30 plus 45, easy peasy, okay? But where you might run into some hairy stuff is this one right here. Which one do you adjust? What's the problem with this? The problem is that neither one of these answers is very close to a friendly 10. And then this one, even if you get this to a friendly 10, you still are running into some having to add these values together. And it's not necessarily as helpful as we might consider. And then when we get down here, this one would be really difficult to make friendly. So we want to use compensation when it's appropriate to use compensation, when it really is helpful. But we want kids to understand, when is it helpful? When is it not helpful? Which strategy? This is why we want kids to know multiple strategies, because we want them to be able to say when a strategy is efficient or appropriate, and when should I throw that strategy out. This is the ongoing assessment project. That's what OGAP stands for. And this is a progression of how kids acquire additive reasoning. So you'll see, you're welcome to pause and study this a little bit, but kids begin in this direct modeling phase, counting by ones. And then they begin to use some of these strategies, but you'll notice they're inefficient. Then they begin to use models efficiently. And last but not least, they begin to use algorithms. And all of these strategies in this top are good algorithms that fall into one of these categories. The tens and ones algorithm is really seen in this partial sums. The incrementing algorithm is really seen in this transparent algorithm here. And the compensation is seen here. It's called flexible compensation. The US standard algorithm, where does it fall? What are we really doing? And believe it or not, the US standard algorithm is actually incrementing, because what we're doing is we are starting here and thinking about 8 plus 7 and we get 15, but we're still, it's still 15 is being split there, and we're going 15 and some more. So it's a version of incrementing. It is, like I said, it's a shortcut version. These three categories really are about kids' conceptual understanding. This US traditional algorithm is a shorthand version of, and connected to partial sums, but like I said, it's really kind of a bridge between transparent algorithms, incrementing, and tens and ones, the place value. All right. If you have questions for me, feel free to email me at, this is my email address at work. If you're willing to scan this QR code and fill out the survey to let me know if this was a helpful video, I would greatly appreciate that. If there is ever anything I can do for you, please let me know. Thank you.